today astronomy is physics, right? It's astrophysics, it's applied physics, using the physics to answer fundamental questions about the universe. And that is the coolest thing ever, right? I don't care that Pluto's no longer called a planet. Call it what you want, I don't care. It's a body that got formed.
Why are we here?
Why are we here? Is that a very large scale question, or do we, right now, why are students here? I'm the first person in the history of the world to see that source. Yes, my name is Professor Looney, and I teach a class on extraterrestrial life and UFOs, and I think that's always weird. And then the universe inflated, and that small, super tiny subparticle change is why we're here. The next fundamental humankind discovery. The first one was we're not the center of the solar system. Okay. The second one was we're not the center of the galaxy. The third one is not the center of the universe. The fourth one, the fundamental one, is we're not alone. That, to me, is the fundamental question left for humankind. I'm not a big believer in the hostile aliens. I think that to be a truly advanced civilization, you have to have curiosity, so I hope that they would also evolve a curiosity.
Where do you see your place in the universe?
Where do I see my place? That's a difficult question, I think.
Whoa, where am I? I'm in the universe, but before we get there, let me tell you about what astronomy is. Astronomy is not just looking at pretty pictures in the sky. The real work is actually building the tools and the methods to turn faint signals into evidence. And Professor Looney has spent his life doing exactly that. In this conversation, we talked to him about astronomy, but not just as, dots in the sky, but about the work that it takes to build those tools, where the universe comes from, and things like Dyson spheres, why we need to build a telescope on the moon, and whether the next great scientific discovery would be finding life beyond Earth. One thing that really stuck out for me in this conversation is, if you imagine a star, you can imagine something in your head. It might be wrong, but there's some sort of visual representation in your head. If I were to ask you, imagine the universe, you can't. There's no visual representation of the universe. And that actually reminded me of This Is Water by David Foster Wallace. And the story goes like this. There's an older fish, and he swings by these two young fish, and the older fish asks, "Morning, boys, how's the water?" The two young fish, they look at each other. They don't really know how to answer, so they continue swimming. And after a while, one of the fish looks at the other one, and he says, "What the hell is water?" So let me ask you now, what the hell is the universe? The things that are most fundamental are often the hardest to see. And it really makes you wonder, should we even be trying to find other civilizations out there? What is the universe? And lastly here, we talked about something that I will never forget, and I think we should be keeping in mind, is that in the end, a truly advanced civilization, whether that it is human, alien, or artificial, is defined by one thing and one thing only. And that is curiosity. Enjoy.
How do you decide what research is like good or like better than?
That's a good question. In astronomy, it's usually the coolest, newest telescope. Right now, JWST is hot right now. Mm-hmm. So it's actually, often it's what the new telescopes are doing, and if you're doing theory, it's making predictions of what they're going to see. We're astronomy, right? So we're a little different. We're science from afar, right? We can't touch, unlike most departments in science, that you can touch what you're studying. We can't. It's far away. So for us, we're always looking to get the new instrument to detect the new thing that's far away that no one's ever seen before, because that's the coolest stuff. And so having access to the newest, greatest is always the hard part.
They're already building the next one, right?
Not really yet. Depends what you mean by the next one. The next space telescope. There is a next space telescope. It's being discussed for a decade now, probably, but it's a simple, cheaper mission. It's actually a leftover spy satellite. That's basically a Hubble they had for free laying around. So whenever you do a space mission, you always build one plus you build a spare, because something happens to the first one. It costs a lot. So they had a spare mirror that was for a spy satellite that was basically exactly like the Hubble, and so they said we can use that, and so that's the next generation it was called W First. What's it called now? I forgot the new name. Not my field.
Satellites. Would you ever want to go to space?
I would. Yeah, I used to launch space shuttles. I used to be a system engineer at NASA, Kennedy Space Center, for a while, and I always thought that was fun. I would have done it when I was younger. I'm not sure now. I hurt my knee running yesterday, so.
Were there any other universities you were considering, or was this your?
I was shortlisted at Michigan, Hawaii, here. That's the three major ones, but Illinois was made me an offer. The others didn't.
Like being in the department for so long, what do you think? Like being on the other side now. Being the one actually making those decisions, what does it feel like, and how does your perspective of you being in that other spot helping you now be a better?
Oh, that's an interesting question. So, I think, and asked an actual student for verification on this, but I think it's more about making the experience better for them, because I was a physics graduate student and it sucked. I had to take a qualifying exam to meet the PhD candidacy, and it was kind of the worst time of my life. And I'm not the kind of person that, I went through it, so you have to go through it. I don't like that. And so I want to make it better and more inclusive. I want to bring people into astronomy, particularly, because astronomy is the coolest science. It just is. I think that's obviously demonstrable. And so really, it's for me to probably bring students in and make it accessible to them. And I really try to make it less as a gatekeeper and more of bringing in inclusiveness and trying to include as many people who really want to be there and really need that initiative to make astronomy a better place. That's, to me, the fundamental thing. When you come into a field, do you make it a better place while you're there? And I think that's how one of the ways I do that.
I think that's a good mindset to have, because you can have the opposite effect too, right? Because
definitely.
You went through the system and you're like, okay, no, I went through it and it worked out for me.
Now you have to suffer too.
Yes.
Yeah. I had that experience with my, when I first came as a professor. They were like, you may get tenure, but you might not. It's really hard to get tenure. And so you may not make it here at Illinois. And the truth is that if you get hired as a professor, typically you will make it if you do the same work you did to get here. If you keep doing what you're doing, you'll do well, right? But that day it's more of a gatekeeping, and I didn't like that. That's true everywhere. I mean, some places are really bad. Illinois is actually really great at that. We've done a great job, I think, of transforming how we approach the process overall.
When you were a professor, were you giving?
Well, I still am.
Right. Before you were the rector.
Yeah. Okay. Yeah.
Did you give more priority to your research or your job as a professor? What do you consider yourself first?
This is not the right answer, probably, but the first answer is always going to be research. That's what we do, why we do, why we're here in the first place. It's why we do the work, why we work 80 hours a week or whatever it is. It's the research that drives us, because that's the really interesting and cool thing. Students are awesome and amazing and fun, and that's also a joy, but it's a separate kind of joy. And also, the more I do in research, the more I know about my research, the more students, the more I'm able to share that information with students. And so having cutting-edge astronomers be your professor or whatever field it is, that to me is an essential part of making a great R1 university like Illinois even more special. So for me, it's 50-50 really, the research and students and teaching, before I had to do chairship and administration things.
What's R1?
R1 is a level of university. It's a research level 1 university.
Okay.
It's what Illinois is most. It's based on how much funding you have from federal sources. but we're an R1 university. And that means that, for example, my department, our faculty teach one class a semester versus 2 or 3 that you might at a more teaching university. So we're expected to have a lot more research and bring in grants and bring in funding.
So you said you guys are here to do research, but why are we here?
Why are we here? Is that a very large scale question, or do we, right now, why are students here?
Up to you.
I'm not sure which way I want to go. You give me a hint. What do you want?
Let's start with the students, and then let's start with the
Okay.
actual question.
Okay, because that's a bigger question. That's a hard question. So why are students here? So students, I think, here to learn the fundamentals about and techniques in my case, to be an astronomer, right? We need to learn the basics. How do you use science? What does science mean? How does science actually get applied? And not this stuff that's about the scientific method. I'm talking more about how to intuitively use physics. For us, today astronomy is physics, right? It's astrophysics, it's applied physics, using the physics to answer fundamental questions about the universe. And that is the coolest thing ever, right? Is to ask questions that are fundamentally huge in our mind. Like, why do galaxies happen? Why do stars get born? Where do planets come from? What kind of characteristics these have? And we are learning that in a fundamental way by studying these processes and beginning that early on in the undergraduate program. So for me, coming here for an undergraduate student is a fundamental step in making that transition from high school to learning what a scientist really does and training your mind on how to answer the big questions, the fun questions.
What do you think the astronomers of the past who perhaps didn't go to college, how was their approach different to the ones, to like the educated class?
I think that, okay, we should take 5 steps back, because astronomy to many people is sticking an eyeball in a telescope, okay. and that's not true. And that's not really been true for many years. In the very beginning, it arguably was. If you built a small telescope, you're a lord in the UK or something, you could build a very large telescope and use it for the first time and see new features. And you draw pictures and maybe talk about that. But that type of astronomy, that's a very long time ago. It's more of a default process that's no longer true. Today, we're much more likely to discuss why these things are happening. Why do you see this? And predict, much more aggressive in the science approach. So I think that today you need that training, because it's not just the physics. For example, today we're in a new world because we're observing the night sky very quickly, very soon. Every 3 nights we'll observe the night sky using certain telescopes. And so surveys, and now you have millions of objects going off, maybe sometimes getting brighter, getting dimmer, and now you have to find those objects. Maybe it's a supernova going off, maybe it's a black hole eating a star, and you have to understand and find those and then use that criteria to build upon what we know in the past to make predictions and understand the universe better. So today, those requirements are just how science has moved on from what it was in the past, if that makes sense.
If you were you just graduated from high school, would you have studied astronomy as your undergrad?
I didn't.
No. Yeah, I know. But like, would you have studied it now?
Like
that's a hard question, because I'm a first generation college student, and I came from a low income background, and I didn't know what science was. I didn't know what astronomy really was. I didn't have access to Netflix or YouTube or whatnot. So I didn't really know much about it. I had learned a bit here and there, but my main objective going to college was to get a job. So I went into electrical engineering as my undergraduate. In fact, I've not really had an astronomy course in my life, even though I'm professor and chair of astronomy. It's just how it worked out. I've built my career in a very different pathway. But that was a hard pathway, and I'm trying to make a pathway better for others. My pathway was a little weird. I've electrical engineering and physics degree, and then leading into astronomy. I was always interested in astronomy, but I was never thought of it seriously as a career path. If I knew about astronomy today, I would have chosen astronomy indeed, because astronomy, again, is by far the coolest science. We're doing the neatest things. I'm looking at objects. I like to observe young stars, right? Baby stars that are just beginning to form. You know, the cradle of star formation, the cradle of life, if you will. And on my screen can pop up a new source, it happens frequently, that no one in the entire world has ever seen before. No one. I'm the first person in the history of the world to see that source. That is cool, right? That's the first time, and not only is it the first time it's been seen, it's the first time it's been trying to be understood. And that process of learning new things, experiencing that, the feeling you get from the first time seeing these objects and trying to be the first person to understand them is a feeling that you really can't recreate. It's an engagement in humanity's understanding of itself, and I just find that super cool.
Would you want a star to be named after you?
I don't care about that. I think it'd be silly to have. My name is silly enough as it is. Yes, my name is Professor Looney, and I teach a class on extraterrestrial life and UFOs, and I think that's always weird. Students never comment on it, but I think that's where having my name on a star is irrelevant to me. I don't care. In fact, we actually have processes on how you name things, and typically it's something very boring, like IRAS 16293 minus 2422A. So
is it more based on where exactly you're finding it in the sky?
it's coordinates, typically, yeah. Then we don't normally do, you don't get to name it after, if you find a new star, you don't get to name it after yourself. There's actually a defined process that we have. Astronomy already has weirdness with names as it is. There's so many names out there for strange things. The brightest massive star is a O star, and then OB, and so forth. And it's just a weird process, historical. A lot of astronomy is historical. We've been around for so long, and the naming processes are a bit obscure and strange, so I don't want to make it stranger.
Is there like a holy grail of what everyone is looking to find?
Each subfield is different. Astronomy, we break into multiple fields. So I do star formation. Some people do cosmology. Some people do galaxy evolution. Some people do cosmology, the origin of the universe. And so each field is going to have a little different. And for me, it's trying to discover how planets form in a way, how stars turn into and planets together really form. Because remember, stars are these giant balls of gas in space, but the planets around them are extremely interesting. Mm-hmm. And those planets are the leftovers. When a star forms in this cloud of gas and dust, it's by gravity being forced to collapse down, and then a small percentage, less than 1% of the material are the planets around them. It's like eating a Thanksgiving dinner or eating a big dinner and looking for the crumbs on the floor. I look for the crumbs. Those crumbs are the beginning of stars, beginning of planets, the leftovers of star formation. The part that didn't make it into the mouth, that's kind of the parts I'm interested in. So that's the process in which I can understand how star formation occurs and how that leads to planet formation in the future. And I find that extremely exciting.
Go ahead.
What is a star?
What is a star? So a star is like our sun. It's a ball of gas that is very hot, and so in the center, because of pressure, it's hot enough to make fusion happen. And so internally it's being heated, and then that heat makes its way out and turns into light that then can be enjoyed for us on a beach.
Why is it moving? Or
Why is it moving?
I mean, sometimes some stars, they seem to be moving. I don't know if they do, but...
All stars move.
Right.
All stars move. Not from our perspective, you're not going to really notice that. Most stars are very, very, very far away. They're crazy far away, and so every night they rotate with the sky. The sky rotates because the Earth rotates, and the stars move from east to west, just like rise and set of objects. But they're far away. But they are moving. Typically, they move around our galaxy. So our galaxy, the Milky Way galaxy, is a collection of stars, gas, dust, and neutron stars and other things. And they all more or less rotate around the center of our galaxy, which has a supermassive black hole in the center. And that motion, it comes naturally from how materials moving around the center of our galaxy. And so stars do move that, and sometimes they also move. For example, our stars moves a little bit because of Jupiter. So Jupiter is a mass. It's not very massive compared to the sun, but it's a significant mass. And so the sun wobbles a little bit back and forth. And if you were on another star and you're an astronomer looking at our system, you would actually see it wobble around a little bit. And from that, you would infer that it has planets, which is how we infer that many other stars have planets.
Why is everything moving in this direction and not necessarily in the up and down?
Yeah, so there's some natural predetermined motion that comes of how angular momentum is conserved. This rotation is conserved, and so when material fell into the early galaxy, that's the direction it was happening. Now, if you have two galaxies collide, they can mess up the motions, and you can actually have gas going in different directions. In fact, we have the gas mostly is going this, but there is material up above and below the plane that is moving in a different direction. That's more of a random motions. And you'll see that in elliptical galaxies, for example. But our galaxy is a spiral galaxy, which means it has a well-defined velocity field in the direction of the plane. Not my field, but it's still, I know a lot about it.
So what are you excited about right now?
So my interesting right now is looking at how baby stars form. So I'm looking at the very first steps of baby stars. So I'm looking at, there's a cloud of gas. It's collapsing down due to gravity. It's supported a little bit by temperature, a little bit by magnetic fields running through the galaxy. It's collapsing, and it's beginning to form a baby star. And I'm interested in how that process works, because in the very center, it's going to form a little disk. And then surrounded that disk is a large envelope. There's these giant outflows being blown into the interstellar medium. And I'm looking at how that disk forms, because that disk, in this very early stage, I'm talking about a star that's only maybe 100,000 years old. So it's just started to form. It's not fusing yet. It's not a star yet. It's a protostar. It's beginning to form. And you have a baby star with this little disk around it, and that disk is moving. And I'm interested in how does that disk evolve, because that's where planets form. And so I'm really interested in that material. It's not a star itself. It's just the gas and dust around the star, how it's moving and how it evolves with time.
Can that rate be accelerated by anything or slowed down?
It can be accelerated and slowed down by some things. For example, turbulence can make a difference. This turbulence can do both. It can slow down the process, but it also can make it hasten the process. Magnetic fields can slow things down, but also can regulate star formation. That's the two major components that will change the star formation rate. But also, you can think of if you lived in a cloud and then a star explodes nearby, that can clearly cause an impact and will either disrupt, or it could actually start formation of other stars. In fact, I think that the sun was born in a large cluster with other brother and sister stars, and a supernova went off, and we have some evidence that a supernova went off nearby us when we were forming, and we're actually from a cluster. It's unusual for stars to form by themselves, actually. So it'd be kind of weird if we formed by ourselves. We probably formed in a small cluster of other stars, but it wasn't a very massive cluster, which means that as time went over, it kind of just slowly dissolved. And so our other siblings are in the Milky Way galaxy somewhere, but not necessarily nearby. But there are siblings that were born at the same time we were, more or less.
Can you trace that? Can you know who?
You can trace it a little bit, but it gets very difficult very fast, because you have other stars creating other effects, and exactly what direction they're moving from. It's hard to take the film backwards and watch how the stars change. You can try, and some people have tried, but you will never know exactly which ones.
Is there such a thing as a base case? Meaning, because once you start going down, okay, like the sun came from this and the galaxy came from this, and you seem to be going into infinite recursion
until the Big Bang.
But even then, people say like there was something before or whatever.
Well, we can't say that.
Okay.
I mean, scientifically, we can't. The likelihood is that we don't know what happened before the Big Bang, because our science breaks down at that point, basically. So falling it past that. Now, there are other ideas that you could have multiple Big Bangs, a multiverse, if you will, not necessarily like the Marvel multiverse, but a multiverse similar maybe, where you might have multiple universes in some 13-dimensional space or something, but we don't know about that. Scientifically, all I want to say is that we can go down to very small times after the Big Bang happened, and that after that we're not sure what happened, or before that rather, we don't know what happened.
What's the role of hydrogen in baby stars?
What's the role?
Of hydrogen.
So hydrogen is most of the universe. Most of the universe is, from the Big Bang, is just simple hydrogen. There's some contaminants, if you will, like the stuff we're walking on. This Earth is mostly a small contaminant. It makes up a very small percentage of material in the universe. Most material is hydrogen. And so hydrogen itself is the most abundant molecule because it's just a proton and an electron. And those protons are what makes up molecular clouds. And so when you begin to form a star, most of the physics that's happening is going to be occurring because of how molecules are how molecules are forming and how molecules are radiating material. Hydrogen is not great at that because it only has certain transitions, but we use hydrogen because it's going to fundamentally turn into the major fusion device, right? When you begin to form a star and it begins to fuse, that's going to take 10 million years. I mean, I'm only looking at the first 100,000 years of the stuff I do, but forming a star is going to take about 10 million years for a low mass star like our sun. And after that 10 million years, that's when it gets hot enough because it builds and builds and builds and builds and gets hotter and hotter in the center. And the center gets hot enough for fusion to happen with hydrogen. So hydrogen, of course, gets stripped at that point. It's just protons, truthfully. And they get banged to clock. They get hot enough. They get close enough to fuse and form form helium and so forth. And that process is essential to life in the universe as we know it because you need to start the process. And that life probably needs a star to have the heat and energy that you need for life to occur. So hydrogen is a fundamental aspect of not only the Big Bang, is what first happened, but it's the process in which we form stars, and eventually we're going to run out of it. We're going to run out of gas in the future, and the universe as a whole, and that's still very, very, very far away from now. But when that does happen, there'll be no more stars at some point because stars will no longer be able to form because we'll run out of gas.
Would that affect anything?
Everything. I mean, if humans are still around, okay, so humans have a problem with our own star, right? Our star is going to get a little bigger, a little brighter as we move along, and in about 1 billion years from now or so, the sun will be hot enough that our oceans will begin to evaporate and disappear. Not really boil, but the water comes up in the atmosphere, breaks apart, and the hydrogen goes away, and you no longer. So in about 1 billion years, we're in trouble as a species. Maybe before that because of global warming or pandemics or whatnot, right? But in about 1 billion years, we're astronomically at least in trouble, and you'd have to move to another star if you want the human race to survive. And if you think human race should be an advanced civilization, that means we have to eventually be able to go interstellar and move to other stars. And then eventually, you might keep doing that. You might think humankind can keep moving out to other stars, but eventually, there will be no other stars left. We're talking trillions of years, though, a very long time from now. And you may argue, will humankind last that long in the first place?
The great filter.
Yeah, but, great filter.
You mentioned that the astronomy is the coolest science.
It's the coolest science, demonstratively, yeah.
So what I find coolest about astronomy is how, like, the scale of astronomy, because first you go very big and then you go very small quickly and back and forth, and that, that going back and forth is something very rare because usually in physics, it's, medium scale and sometimes large scale. Biology, very small.
Yeah.
Chemistry, again, very small. But astronomy, just like you go up and you zoom out and you zoom in and back and forth and you try to understand what happens.
Yeah, it's kind of, it doesn't fit in your head, does it? We have scales that don't make sense. They're so big and so small all at once. We make up these terms, we call it light years or megaparsecs, and then we have AU, and then suddenly we're down to the size of molecules or neutrons in a star, right? The scale is amazing, and so it does make it difficult for us to, I think most astronomers will say, I understand it, but really it doesn't fit in our heads. The scales are too large. And that is a barrier in how we teach, right? To be able to talk about these scales, we do jump back and forth a lot because to us they're kind of critical. One scale feeds into the next scale, feeds into the next scale. But to bring that across to students is very difficult. And we often have problems trying to discuss that type of scale. So it is difficult for astronomy, but it's also a very exciting aspect of it because we're able to jump back and forth, and you can see the impact of how one star may affect the entire galaxy in some ways or affect civilization as we know it, and that's kind of fun too. So I do like that aspect.
Do you believe in the butterfly effect?
Butterfly effect, specifically the time travel idea, you mean butterfly effect?
No,
or
where like any small action.
Oh yeah, I think whether it's going back in time or not, I suppose the butterfly these small things can cause large impacts, and the likelihood that it's going to cause a statistically not large impact may be doubtful. But all of that said, I see this on a daily basis in some ways, right? And I'll go back to students. I have a student who came to talk to me one day. And the next thing I know, he's working with me. And next thing, he's going to graduate school. And then he's meeting his partner at graduate school. And his whole life is changed by just coming to talk to me, right? And that might affect not just him, but generations of people in some way, because I'm teaching him, he's teaching others. And that effect we see all the time as faculty. And it's one of the great things about being a professor in some ways, is that impact that you have on others and that you can trace kind of directly. And so because of that, I think, I really believe in the sort of small impacts can have a greater impact. And then we can take it a step further and say, what about, again, diversifying astronomy overall? It's that introduction, mentoring a student, believing in that student, helping them understand how to navigate the process of astronomy or academia or whatever. You see that having a long-term effect as a professor, which is a great immediate response for us. But that also sort of leads me to think that the butterfly effect that you may be thinking of is something that we have to consider, yeah.
Do you think it scales to the entire universe?
No, probably not. Well, the entire universe may be a long shot, but remember, so the galaxy we're in now, the Milky Way, where did it come from? It's kind of the question you were asking a bit. Where did it come from? Fundamentally, we can trace that back to fluctuations in this thing called the cosmic microwave background. Cosmic microwave background is sort of this last region of scattering after the Big Bang. Where does that come? We can trace it back to quarks, small subatomic particles that have a little bit of excess moving around, and then the universe inflated. And that small, super tiny subparticle change is why we're here. If that had not happened, the universe would be smooth, and there would be no galaxies. There would be no star formation, because you need a little bit of some differences in the universe to make the universe sort of begin and create galaxies, create stars, and then eventually create life. So these small effects are measurable, and that's what we think of how galaxies formed. Well, this comes back to, there's many ways to think about this. There's the puddle analogy, which is where you have a puddle, and one person might argue, sometimes religiously, for other reasons too, oh, that puddle formed perfectly. That hole where the puddle is at is perfectly formed for that puddle. Isn't that amazing? That's kind of the same question. And you might take that to the anthropomorphic universe question, which is, oh, we're here, we're talking, therefore we live in a universe that's good for life, right? It's the same kind of question. Or in case of the puddle or case of life on Earth fits Earth perfectly because life on Earth evolved on Earth, right? It had to fill niches that made life turn eventually into intelligence on this planet. So of course, life on this planet fits perfectly with this planet. It makes you seem like this is the perfect planet for life because life on this planet fits so perfectly. It's the same as the puddle. Because we evolved here, we think this is essential for life, that this planet is essential for life, where in reality, who knows what's essential for life? Life formed on this planet like that. And as soon as giant rocks stopped falling from the sky, life happened on this planet. Well, I say that, it's something like 100 million years, but 100 million years fast. That's very fast, though. And so, again, coming back to that anthropomorphic idea of the universe, does that mean that our universe is perfect for life? Well, I don't know. But it is kind of related to the same point.
Why are stars? Why do stars have the shape that they usually have, like the 5 legs?
Yeah, they don't, right?
Right. So
this is coming back to the idea of human interpretation. Now, if you look at the sky, you might see if you kind of squint, you see these sort of lines on stars, and that's more of your optics of your eye. And you look at the sun, of course, you get this weird shape too, but that's more about optics than it is about reality. Stars are going to be spherical always because a sphere, just like why the Earth is a sphere, the gravity's pushing in uniformly from all directions. And in fact, if there wasn't something pushing back, it would it'd get pushed down to a point. On Earth, you have electromagnetic forces pushing back against gravity and makes the Earth round. In the sun, you have fusion pressure, heat pressure really, just the fact that you have hotness in the center. It doesn't have to be fusion, it just is fusion. That pushes back against gravity. But when a hydrogen runs out in the center, then bets are off, you get squashed. New fusion happens and you get a red giant happening because of that. And eventually that runs out and you get pressed down again. And if you have a very massive star, you get pressed into a black hole, which is the absolute ending where gravity wins completely and crushes everything down to a point. That will not happen with our sun because our sun is not massive enough. It will actually turn into a white dwarf, which then has electron degeneracy pressure pushing back against it. So all that's kind of, astronomy is related to everything.
So stars, even though it's spherical, we do have a symbolic.
We have a symbolic rotation, right?
I don't think we have a symbolic representation of the universe.
We don't know.
If you
No.
had to come up with one.
No, well, the universe is hard to have a symbol for since it's everything in. There's nothing outside of our universe. It's everything. So it's really hard to make a representation for that. Why we have a representation? I don't know why the representation. I don't know why that is. Yeah. We also use the word disaster. Do you know what the origin of the word disaster? Bad star. Diaster. It's bad star. So it's a similar, which then of course that's our astrological speaking, right? You had a bad star, that makes it a disaster. But we don't have this representation for, and we have representation for planets, arguably. You might think that's pretty clear. Mostly it's going to look like a Saturn, probably. Oh, sorry, mostly look like Saturn, I think. And the moon isn't obvious because it has the craters. But yeah, nothing. We really have nothing for galaxies, except that we know what galaxies look like today, so we actually make pictures of galaxies. So you probably know if you saw a picture of a galaxy, you probably think that makes sense. It looks more like the Milky Way with spiral arms and so forth.
But it's like 2D.
Yeah, it's 2D for sure. Yeah. Universe is nothing, because it's everything, I guess.
What is gravity? It's a simple question, but I don't know the answer to.
Gravity there's multiple levels to that answer.
At the most fundamental level.
It is attraction. It's attraction to mass. Mass attraction to mass is a simple answer. And so if you have this water bottle and you have yourself here, there's some pull between the two. If we were in space, it would eventually come to me. But here it's not, because there's friction on the table, there's air, there's all kinds of issues. So gravity is a relatively weak force, actually, compared to other forces, but it adds up. And so we're standing on this big sphere, and we're not falling off the sphere because the force of our gravity, they're always going to be pointed at each other in terms of the center of gravity. The center of our gravity is pulling down, in this case through a chair, but there is the gravity of the Earth and the center pulling each other. I'm pulling the Earth is pulling me, and that creates the force that we feel. In space, example back to the star formation, you have this big cloud, which may be many solar masses, multiple solar masses, just sitting there, and then gravity is saying, "Hey, you're pulling on each other," and so this little molecule gets poured this molecule, and then that kind of gets expanded and runs away, if you will, sort of a snowball effect, and it all begins pulling in, unless something stops it. What can stop it? Well, you could add heat or turbulence in, and that could stop it. That can make the molecules, instead of getting pulled, they can move apart. Magnetic fields can stop the molecules, can sort of trap the molecules to not let them move. But otherwise, gravity is going to win. That's one of the big questions in our universe is, will gravity win? Will the universe expand, slow down, stop, and then come back? Gravity will win? Or is something else stopping it from doing that? Is there enough energy to make it just slide on forever? And was a big question until the last 20 years, when now we know the universe is doing something completely weird and strange, which is, instead of it just expanding and slowing down, it's expanding, and now it's going faster, which doesn't make sense. We call that dark energy, and we wave it away.
Let's say we find dark energy.
Well, we've already found the effects of dark energy.
Right.
We don't know what's causing it exactly.
And
this is not my field.
Right. And let's say we can find a way to make dark matter. How would that help us?
Dark matter of and by itself, I don't know the answer to that. Dark energy might be interesting because dark energy has this almost anti-gravity effect. And so you could imagine that there might be a possible energy source there. If you knew what it was, if you knew, I'm making this up completely off my cuff, but if you understood what's causing dark energy, you maybe could use it to develop some sort of energy usefulness. What does humankind need? Humankind needs some sort of free energy, cheap energy, right? With cheap energy, we can solve a lot of our problems if we had cheap energy, whether that be fusion energy or whether that be something else we don't know yet, but we need to get off fossil fuels. I think that's pretty obvious. And we need to have something else if we want to be an advanced civilization that is very comfortable. And so we need some sort of cheap energy. So the Department of Energy, for example, funds a lot of astronomy because they're interested in what is dark energy. It has the word energy in it, so maybe that's a good connection for them. But we don't know really what's causing this expansion. It must be something fundamental in the universe. It's more important now than it was at the beginning of the universe, so it's gaining in importance, and we don't know what it is. Most of the universe we don't understand, which is kind of problematic.
Why haven't we built a Dyson sphere?
Why haven't we built a Dyson sphere? A Dyson sphere surrounds the sun and allows
Or a
us to
star.
capture the energy,
Yeah.
or a sun, a star.
Okay, perfect.
Allows you to capture energy by capture the energy of the star and use it. And that's a good way to get free energy out. The problem with a Dyson sphere is that it's an exact sphere centered around a star. It's kind of hard to do. First of all, mathematically, you have to kind of keep it in control. But let's say that's aside. The problem is forces. First of all, you have to build a structure. That's the size of basically 1 AU, the Earth's orbit. And that's hard. It may be arguably impossible currently. So we don't have the current materials to build something like that. The preference currently is to build a so-called Dyson swarm. A Dyson swarm is a number of satellites around the sun. That'd be easier. You collect the light, turn it into electricity, then beam it down with microwaves, for example, down to Earth. That would be one good example. So Dyson spheres cost. And then probably we don't have materials yet. It's just really hard to do. We're not there yet.
Have you ever thought of, so we say that the universe is expanding, right? Have you ever thought of where all that space is coming from? Or do you think, is space created or is space occupied?
This is always a hard problem for all students to understand is how can the universe be, they want a top-down picture or schematic of this, right? The universe is everything. And so if it's expanding, what's it expanding into is kind of the fundamental point you're making there. The space is expanding. We're not expanding. Our galaxy is not expanding. The expansion of the universe is not we're held together by gravity on this planet. Our galaxy is held together by gravity. And gravity is more strongly cohesive than this expansion coefficient that we have. So it's the space between galaxies is indeed getting bigger, and that makes people uncomfortable. Because what does that mean? What's north of the North Pole? It's that same kind of question. And the answer is, yeah, it's getting bigger, but it's not coming from anywhere. And that's hard to fit in your head. Again, this is observable universe. We actually don't know what our universe looks like. We don't know how big our universe is. It probably is infinite, but we can only see out as far as light has traveled in the time that the universe has existed. So we can only see out to the edge of the since more or less 13.8 billion years ago, and that's kind of it. Beyond that, we don't know what's going on. We can't see beyond that. Tomorrow we'll see a little more, tomorrow a little more, but we don't know if the universe is infinite or not. But nonetheless, it is the universe. It is everything. There's nothing else outside the universe that matters to us, and so it's just expanding, and it's hard to fit in your head again. It doesn't make sense. Sorry.
Where do you see your place in the universe?
How do I see my place? That's a difficult question, I think. So I see my place in the universe. I like to discover new things. I actually like teaching. I love teaching. I think it's fun. Even I didn't have to teach when I was chair of the Department of Astronomy. I did it anyway. I just like teaching. It's kind of a fun thing. It's a way to interact with people. I like it. And I like doing the research. So my place is really to help us. I think I don't find myself. I'm not the great discoverer, but I'm making a difference. And I think that's important. Everyone makes a difference and do the best they can. I don't know, that's a strange question.
What would be a better question to make sense of that meaning? Or lack of thereof?
Man, I don't know. I think to me, again, it's more how you're making it a better place. The world a better place, or humanity a better place. How to interact with people, how to interact with the world, how to understand the world better, to me is a fundamental calling. And that's what I like to do.
When you say that making a world a better place, that sounds similar to the universe expanding.
Mm-hmm. It means nothing? What?
No. Not that it means nothing, but like making something better, that usually means, it's like expanding outward.
I'm not sure the universe expanding is making it better, but yeah, I see your point.
like like if you had to, like, what would be the like the most surprising or best scientific discovery if you like about stars?
Oh, no, the most fundamental one is one I'm not really involved with, which is the next fundamental humankind discovery. The first one was we're not the center of the solar system. Okay. The second one was we're not the center of the galaxy. The third one is not the center of the universe. The fourth one, the fundamental one, is we're not alone. That is, I'm not involved in that discovery, but that to me is the fundamental question left for humankind. Is there other life out there? We have not answered that question. We haven't answered it in our own solar system. We're not anywhere close to answering it in our galaxy or anything like that. So that's the next one. If we make that discovery, that is going to blows my mind.
Why aren't you working on this?
I'm working on it indirectly. I'm not working on it directly. It's a SETI experiment. So these experiments, search for extraterrestrial intelligence using radio to look for life. It's a long shot, quite frankly. It's just not something I was directly interested in getting involved with. I'm interested. I learn about it. I keep up with the research, but it's nothing I've myself gone out to pursue, just because it's one of those things that you may spend your whole life with no answer. Right. And that can be frustrating. I'm looking at it from the angle of, I am looking at that question arguably, but I'm looking at it from the question of, are planets common? How do planets form in the first place? Do we expect the molecules that happen on planets to be comparable to what happened here? That's how I'm addressing that question. And I'm addressing it more as an astronomical question versus the direct search for intelligence, which is really hard.
Someone told us once, I forgot who it was, but there were 2 times that we send super strong signals, and if someone saw that signal, they probably would have definitely saw it. So the first one was some Hitler television.
The Olympics.
Right. Mm-hmm. And then the second one was the U.S. and the Soviet Union, like the radars.
Yeah, our radars are still probably the number one way we'll accidentally detect extraterrestrial, because our military radars are still very strong, very focused, but very, very strong. And we did some all the rest of the things we've sent out are kind of just baby attempts, nothing serious. I mean, Doritos sent out a message to the stars. There's been a number of kind of silly ones. And then there's the Arecibo message, was sent out for 3 minutes only towards a globular cluster that's likely not to have life on it because it's so old. So we've not really seriously done anything except for maybe, like you said, a few attempts. Aliens will never be able to watch TV like you might see on The Simpsons or other TV shows. That's not likely. It's just that would take an antenna the size of the moon or something to detect. Even relatively nearby. So it's these one-offs that might be more likely to detect. And we're detecting a lot of these one-offs already in the search for extraterrestrial intelligence. We do see bright signals, not frequently, but often, that come from the stars, but they go away. They don't last very long. What are they? Could be something else. They could be, we do know that there are these radio bursts that happen from some stars once in a while. They could be related to that. They could be actually other military radar. We don't know. But yeah, we're not seriously looking. Well, we're seriously looking now for the first time ever on this Breakthrough Listen project that was started about a few years ago. It's the first time we're seriously looking constantly with some portion of a telescope and sending out things not seriously really ever. And then who has the responsibility to send out messages to the stars? Who gets to say? Does one country get to send out messages? It's a big question, right? Because some people, for example, Hawking, said we should not send out messages because anyone who responds will most likely be hostile. Ask any Native American, you see it can be bad when people come to visit you. We have to keep that in mind. So who has the right to send signals? Who has the right to tell people that they detected a signal in the first place? Really big questions we've not addressed significantly as a species.
Do you think we should?
I don't want to hide messages ever. I think if when message detect, everyone should know. Whether we should send out messages, I think we should. I'm not a big believer in the hostile aliens. I think that detecting, again, because this is such a big fourth transformational aspect, aliens exist, that would be a fundamental change in humanity that we should try. We have to go and try. I'm not too worried about aliens invading us myself. That said, it's hard to do because of money. Sending out messages, that's energy. It's a lot of energy. And you really need to do it for 100 years, maybe even 1,000 years to be serious about it. And that's just not going to happen in today's economy.
What would you put in the message?
That's another fundamental question. Typically, one tries to do math. And the ones we sent in the past are relatively simple messages. The Aristotle message is a very small message, but it had tons of information. It had the population. It had our estimates of our base pairs in our DNA. I'm more interested in just something that's simple that says we're here, that we exist. Please call back when you get a chance.
I think Voyager had that.
Voyager has a disc, golden record.
Playing a song.
You can play it's images and all kinds of things.
Right.
But that was only for publicity. That's not going to. Voyager will never be found by an extraterrestrial civilization. That's just not going to happen. But it was a way for us to. It's important. Why is it important? It's important because we're thinking about the problem. How do we contact other civilizations? What do they need to know? It reflects on. Takes us a step back. We reflect on ourselves. We reflect on our civilization. What's important to us as a civilization, and I think that's. The journey sometimes is important as the destination, and we do that often. I think. And Breakthrough Listen also has a breakthrough message, which is also re-examining another project to examine how we should be sending out messages, and then of course we're trying to do a breakthrough star shot, which is to visit Alpha Centauri.
Do you think it's a worthy place to invest money in? Like not in terms like financially, but as a civilization.
I do think it was part of it being an advanced civilization. If you want to be a truly advanced civilization, you need to do these things. But that said, there are big problems we have: climate change, pandemics, obviously, poverty, equality. All these issues are big, and they have to be weighed with civilization. What we spend our money on. And again, I think a lot of this is going to happen more when we become a more advanced civilization. When we have cheaper energy, basically.
So, a more advanced civilization pretty much equal to just being able to figure out how to have free energy or
cheap energy and not destroying our planet, being able to travel at least locally in the solar system. I'm not sure we'll ever have interstellar travel really or not. It's really hard to travel between stars. It may be impossible, I don't know.
We just need to find a hyperdrive.
We need to find a hyperdrive, but currently new physics doesn't happen like that. So if we had a hyperdrive, yeah.
When you think of the scale of the universe, do thoughts of nihilism ever come across your mind?
What do you mean? Like, this can't ever happen? How do you mean?
But what I mean by that is, the scale is overwhelming.
Depressing, you mean? Depressingly?
Not depressingly, but like it can be depressing and optimistic. I'm talking about I'm just asking you, like, when you think about the universe and your scale in it, do you think that, let's say you did something that you regret, and
happens all the time.
Right. And do you think of it as optimistic nihilism in a way that, okay, I'm gonna die and the universe is gonna move on and this is not gonna matter in the bigger scheme of things, or does it have the opposite effect where the bigger scheme of things just seem to depress you and make you more nihilistic, that nothing really matters?
I don't feel like I have either of those. You can start. So we are I think I've mentioned we are stardust, right? We are parts of stars have exploded. Supernova exploded. Stars have evolved, all to come together and be us. We are, without these stars, enhance the elements. Otherwise we'd just be hydrogen, bringing in carbon and so forth from other stars. We are the leftovers and bits and pieces of other stars. We are the universe trying to figure itself out. We are the representation of the universe in some ways. We're all linked together. We're all brothers and sisters. Humanity is one big elemental aspect of astronomy. And I think of it more as we're trying to figure the universe out. The universe, we're kind of one of the aspects of the universe trying to understand itself in some way. So I'm less in that direction and more of the optimistic version, which is, wow, this is amazing. We're here at this time and we have these brand new tools that no other time in history have we had, these telescopes. We're building 30-meter class telescopes now this is amazing. The technology we have, the ability to see what we see like no other time in history, that's amazing to me. And the fact that we're detecting 4,000, 5,000 planets around the stars today. When I was a kid, we just knew of a couple, of 9 or 10, and then got rid of Pluto, and then whatever. And now we know of all these planets, and to me, that's the aspect I dwell on. I think that way is a little odd, considering all that we are and all that we have. It's quite the opposite for me.
I like to think of it as like neurons in a brain.
Yeah.
Like we're like trying to make these connections, and we're trying to figure out what we're a part of. Like it's just like on a bigger scale, like you are inside the brain.
Right. It's very similar to some analogy in some way, because what is us? Mm-hmm. We're a brain. We're not connected to this world at all. We're only connected through these neurons and through these nerves, and what we're seeing is actually upside down and flipped. And we're missing. Our brain fixes all the errors we have in our eyesight and our understanding of what color dress is that, how our eyes perceive the universe. We're like playing a video game inside this little mass of fat,
Right.
And really understanding the universe is amazing that we're even able to understand our own environment, and yet there we are. And yeah, that's a really direct connection with that sort of brain, and with astronomy specifically. Right? Astronomy, again, we're studying things that are far away that we'll never ever touch, and it's almost the same way in some manner that we're observing our own environment through this process that evolution has provided, where we think we're in the real world, but in some ways we're not. We're encased in the skull, trying to understand the universe through these senses that we have.
How do you celebrate this feeling of life? How do you celebrate life?
I try to get outside a lot. I like to hike in the mountains, and I like to go to beaches, and I like to run in the prairies. It's that connection, especially when the sun is out and it's bright and you feel that warmth on your skin. That again, it's the connection. Everything's astronomy.
And you really take pride in that.
I do. I mean, I've got the best job in the world. It's not well paid, but it's a great job.
In the universe.
The best in the universe. Well, I don't know other alien civilizations, so I can't speak for those. But otherwise, yeah, in the universe, I love it. I love my job. It's perfect.
Do you think the universe is computational? And if so, would that make you more convinced that the whole thing might be a simulation?
Okay, we're going there. Are we going there? The simulation idea? Really? I'm not a big fan of the simulation idea. I mean, I've heard it many times, of course. Maybe you've had people talk about this on your talk show. Although we are removed, and you can make arguments for pro and positive, negative and positive about why you might be in some sort of massive simulation and the fundamental issues that we have with that. I mean, the idea that, right, that once you have one civilization that's advanced enough, the likelihood is you'll be in a simulation, because they'll have a simulation that makes a simulation that makes a simulation that makes a simulation. So statistically, you're in a simulation. I don't buy it. I don't think that I don't believe that kind of computational power is going to really ever exist to make the kind of connections that we have and see and what we measure and so forth. So I'm not buying that idea. But that said, it is interesting to think about that concept of a future, even advanced civilization. I mean, arguably, one of the biggest concerns for us as a civilization is artificial intelligence eventually moving to the singularity. When, as soon as machines can really think, I don't think what we have today is that, of course, but once they can really think, and they can evolve so quickly, that once they are able to be sort of mock biological, right, that they'll be able to evolve like that, and they can instantly make evolution in seconds, what took us millions and millions of years. And that, to me, that will be interesting, because how that fits into our path forward and other civilizations' path forward is extremely exciting, right, in some ways, because the possibility of artificial life expands our universe in many ways, because they have none of the problems that I'm worried about for interstellar travel. They don't have that problem, right? And so it opens a lot. So I'm more interested in that side, which is not that we're a simulation, but that life itself can eventually become a simulation through artificial means, and that would be very exciting and very quick evolution. And what that might mean for us as a species, I'm not sure it's bad or it's good. That to me is exciting and interesting.
imagine we are in this singularity right now.
We're
and-
not. We're not though.
No,
Nowhere
but
close.
just
Okay.
imagine, just
Okay.
suppose, like, may not right now, but in 50 years, 100 years,
Okay.
whatever.
Let's assume.
And robots and artificial intelligence are a lot more advanced than humans.
Sure.
How would they approach astronomy, if you had to guess?
Ooh, I don't know. I think that to be a truly advanced civilization, you have to have curiosity. So I hope that they would also evolve a curiosity. Otherwise, you're not going to make any advances, right? You need to have that curiosity to look and explore things that might seem like dead ends, things that might seem completely worthless. I mean, I study star formation. Is that any use to civilization, any use to people? Probably not in some ways, but in other ways it is, because again, it's answering that fundamental question: who are we? What are we? What are we doing in this universe? And so I would have to think, and maybe I'm wrong, I would have to think that any cognizant advanced civilization would still have that desire to push the boundaries of science. Now, science might move a lot faster, it might move in a different direction, but I have to believe that that process would still be there, and they would still want to do astronomy. And they'd probably still be the luckiest robots, the ones that get to do astronomy.
At the very,
End of, yeah.
Yeah.
Yes.
Do you think knowledge is discovered or invented?
Knowledge is probably both. I think it's probably 50-50 in some cases. I think there's a lot of discovery. For astronomy, there's a lot of discovery. For our science is pushed by new telescopes usually, or new computational techniques. That's where we have our big breakthroughs. That can mean that you have very punctuated advances, right? You suddenly have a ton of things happen. You might call it not stagnation, but just kind of leveling off for a while, and then more discoveries of that punctuated equilibrium kind of model. And so I think in that case you would have maybe I'm not understanding your question directly, but I think that because of that we get these extra improvements of our knowledge overall. I'm not sure I addressed your question correctly, not there, but.
Right. So yeah, I mean, I always think that, I don't know if it's a good question or not, but so like everything that we're learning today, or let's say we're discovering, can we say that we invented that knowledge, or do you think that's just something that just comprises, it's in the fabric of the universe that we're just discovering?
We're discovering it, but we invented the techniques to get to it, right? I mean, it's not, you can't just discover those quarks without inventing the technology to get down and measure that sort of energy scale.
Right.
The same with astronomy. You need to have that the invention, the desire for curiosity to push and know what you're looking and discover these ways to, or invent ways to do discoveries, I guess. Mm-hmm. So it's more of a building on, as I'm saying, again, these periods suddenly have lots of results because you've invented the technology to do the discovery in the first place.
If you had to build a telescope today, let's say you had all the money that you wanted to build the most perfect telescope, all the permissions, grant, land, how would you design it?
I'd probably big radio telescope on the moon.
Okay. And why?
On the far side of the moon, it's blocked by human emission, and you can build bigger on the moon because there's less gravity. Mm-hmm. So it'd be the easiest, and that'd be the best place to build a really nice big telescope. We can't really build many big telescopes, radio telescopes on the Earth because of gravity, because of other issues. We build interferometers, which are nice, and I use those all the time. But a nice big telescope on the moon would be fun. I think you get a lot more stability in it. That gives you more noise sensitivity. It would give you a bigger surface area. You would point, you would have the interference of the Earth. There's lots of benefits. And so I think the discoveries would be amazing. Specifically, I'm interested in polarization. Now I'm interested. My interests moving back and forth as I change in my research. Right now, I'm really interested in polarization of light from dust and disks around young stars, because I don't understand it, and so I've been pushing a lot in that direction lately.
And what kind of features would you want it to have?
Big, really big telescope. Bigger is better in that case. Astronomy is one of those cases. Bigger is better when it's big. More sensitive, stable, those kind of things, and it has to do work in the wavelength range I'm interested in, which is usually in the wavelength you don't really need the moon for, truthfully. But I'm more interested in making a big single dish telescope. It would be fun.
And you said radio frequency?
I like because I do radio. Okay. The objects I look at, baby stars, you can't see except in the sort of or a far infrared actually. A far infrared telescope is really nice. We don't have one of those at all right now. We're kind of broken. Our far infrared telescopes were Sophia, which was an airplane that flies with NASA airplane that was I worked on that for many years. It just got canceled. So I forgot about that. I might do a far infrared telescope actually. A big far infrared telescope would be nice too. And it can be cooled. A big far infrared telescope might be my actual bigger choice then actually, now I think about it. That would cost a lot of money. But if money's no object, yeah, sure, we'll do that. If you cool the telescope, because in the far infrared, a telescope is like a light bulb. It just glows in the far infrared. It's too hot. It glows. So you've got to cool it down to make it detect weak signals. And so if you could cool it down to a couple Kelvin, that'd be great.
Right, and like putting
That's
it in
impossible.
space would be perfect.
Yeah, space is perfect. Yeah.
Tell us more about your experience at NASA.
Which one? I worked at many NASAs.
All of them.
So I first worked as my undergraduate electrical engineering, as I said before, and I worked launching space shuttles at Kennedy Space Center, which was a lot of fun. I was a system engineer, worked for DPS, data processing systems on the shuttle, and we did the main computers and the processing. It was interesting to learn how old everything was. All technology that flies in space is typically kind of old because it has to be for manned flight because it has to be proven. So it's fun to launch shuttles. I was in the launch room for many shuttle launches. I was there during some very tough times. We were having some issues on launch. It was exciting to be in the launch room and about cancellation. We're looking up data. That was a lot of fun. Being out there, I was the closest you can be for a shuttle launch. I was on one of the crawlers, the big crawlers that move the rockets out. I actually walked next to that. That was also cool. But I was out there, and the shuttle launches, and my badge is jumping up and down, and the noise is incredible. And watching this thing take off, it's just super fun to watch. But I decided to go to grad school after that, even though that was super cool, and they wanted me to stay. It was engineering work. It was a lot of paperwork. It wasn't. The actual work itself wasn't particularly fun. Then I went to graduate school and I decided I wanted to do gravitational waves. And then I took my first gravitational wave course and decided I didn't want to do that. But I worked at NASA Goddard for a summer, helping build a gamma ray telescope, receipt detector system. So I did that for a while at Goddard, then decided I wanted to go back to radio waves because I did radio waves as a senior thesis as an electrical engineer. And happened to be a newspaper article in the school paper about this new radio telescope that they're built that Maryland and Illinois were involved with. And so I went to that professor and said, hey, this is cool, I want to do this. And that's how I got back into radio, and I've been radio since. And then I've worked with NASA in terms of Sophia. Sophia is, again, 747 SP airplane that flew at 50,000 feet, 500 miles an hour, but still had a telescope that pointed to a star to a arcsecond of accuracy, which is amazing. It's just amazing to watch that work. And I helped build with a German group. I did a postdoc in Max Planck in Munich. Build a far-infrared spectrometer for Sophia. And I flew with Sophia, I think 5 times or so. And I actually got to sit it's a 747, I got to sit in the cockpit during takeoff and landing. And that was a lot of fun. That's a really interesting experience to be in a 747 during takeoff. I had never done that before. So I've been lots of things, and all of them were all great and fun. I enjoyed all of them. They're all just different experiences that I never thought I would have had, except I went into astronomy.
How was the experience at Max Planck?
Max Planck was fun because Max Planck had, it's a pure research, right? You're doing research 100% of the time. There's no teaching, which was kind of weird for me. But it had money. And we're doing some great fun stuff, and I had some really great people working with me, and so that was a lot of fun to work on an experiment. The experiment was slow because of NASA, but it was a lot of fun. I really enjoyed living in Munich for 4 years. Munich's a great city, and Oktoberfest was a lot of fun.
How do you think that changed you from when you first entered Munich and after you left after 4 years?
So I again came from a relatively small place in Florida. And moving to Max Planck was a major shift for me. I went there with 2 suitcases and a bike, moved to Munich after graduate school. I just got my PhD, and I didn't speak any German. Mm-hmm. I moved there. I didn't have time to learn German. I was busy working on my PhD thesis. I get there. I almost know no German. They hired a driver to take me to the new place I had. They luckily picked me up at the airport. He didn't speak English. So it just changes your mindset. I mean, living in an international place, it was a great experience. I loved it overall. I might have stayed in Munich if I had a chance because it was a lovely city. And the beer is excellent.
And in essence, it gives you a sense of it humbles yourself because it
humbles,
gives you that scale of
viewpoint, a different viewpoint. Yeah, it's like astronomy does. It gives you a different viewpoint on yourself that you might not have otherwise, and it makes you question your everything you thought of before, your viewpoints that you grew up with, perhaps. Now, you see this in all students who come here. International have the same effect. You're slightly different. It's a completely different perspective. It gives you a completely different feeling yourself. It widens your brain, your mind, and you think differently in the end. And that's really a critical part of being human, right?
I always think how can you make these experiences more accessible to everyone? Because I'm sure like everyone would benefit just by that feeling of maybe feeling small in a new place, but still getting that new perspective.
Oh, definitely. I think so, and it's difficult because of a question of funding, right? I couldn't afford to go to a major school when I was an undergraduate. I went to a University of South Florida because I could afford it. I could never afford it. I mean, now we could. University of Illinois has a special program for economically privileged students, but I had no approach to that back then. But college was a lot cheaper when I went to college. So opening that experience up and providing that sort of programs for people to do it is a difficult problem. It's something that we worry about in the astronomy department all the time, how to make the experiences, research, getting undergraduates involved in research, for example, how to lower these boundaries or these barriers is always important.
And especially someone that perhaps has a similar background as yours, that perhaps they don't have all the luxuries, and astronomy may not be an option for them because they will have to do engineering because of a job.
They want to get a job, and
astronomy is not a job major.
That's not true. Actually, astronomy in LAS is one of the top paying majors. Well, believe it or not, because our students typically have to learn a lot of programming, so they actually are typically very good at Python. So our students do quite well, actually, in terms of liberal arts and sciences. We're one of the top few departments in average salary for our graduates, surprisingly enough. About 50% of our undergraduates go into industry, and about 50% try to go to graduate school. So we have a lot who go into industry, often into healthcare, interesting enough. The University of Illinois is one of the top 5 programs in the country for astronomy, one of the biggest departments for undergraduates in the country. And we do, I think, a good job of educating our undergraduates and providing experiences for them. But we are limited because of research. It's hard to get students involved in research easily because we have so many faculty. And we have for us, a huge program. We have 160 astronomy majors, which is large for astronomy. Astronomy is one of the most competitive markets, jobs out there, unfortunately. It's very hard to get into graduate school. We have, for example, 250 applications for 5 slots in graduate school, so it's pretty difficult to get into graduate school. And then you have to get a postdoc, and then you have to get a faculty job. It's very competitive. It's maybe 3,000 of order 3,000 professional astronomers in the country. It's not very many. And then probably 3,000 in Europe, which is the two biggest locations for astronomers. Astronomers are very underrepresented in the world. We're a very small group. How many astronomers does one need? I guess one can ask that question too.
How do admissions work?
Undergraduate or graduate?
At the astronomy level.
At the graduate level, we don't really control we don't really control the undergraduate too much. We control the graduate. We have very little control on the graduate admissions process here in Illinois. I don't know what the other departments do. Graduate admissions we have complete control over. And we get applications, we look at them all, and we do interviews, and we decide who has the most grit to sort of, undergraduate and graduate school are very different beasts. Undergraduates, you kind of get told, take this, take this, take this. Graduate school, you take this and then do something. And then you've got to make your own plan. You've got to be very self-driven. A lot of people don't like graduate school, and they don't, especially in a program like mine where we go straight to PhD. There's not really a master's program as such. It's just sort of straight into the PhD program. And so it is a little difficult. We get, like I said, hundreds of applicants, and we try to narrow it down to sort of 5-ish in the end to come and do work with us because we only have so many students we can support. We try to support students. Once you come to us for graduate school, you don't pay anything, right? You get paid. You go through TA positions or research positions, and we sort of expect to support you your entire 5 to 6 years. So it's a big commitment for us. It's a big commitment for the student. So graduate school is very competitive. It's very difficult to get into graduate school today. You almost need to have a paper published as an undergraduate to get into graduate school in some cases, in many cases. So we are cognizant of that, and we are trying very careful when we work with people. We try to look for not just we don't look for academic excellence only. If you get a 4.0 average, it's nice for you, but that's not usually a good indication you can do well in this graduate school for us. We look at a lots of holistic view of your application, if that's what you mean.
And how do you identify grit?
By experiences, which may be a problem, but experiences. What have they done? I don't care if you've done something in a different field. I don't care. Some of our students come in, they're electrical engineering students. They've never had a astronomy course at all. But I'm looking at what they've done. What have you done outside of what have you done taking your academic tool set? Because academics, your classes, are really just a tool set that you have. How did you use those tools? What have you done with those tools that made a difference, that you've done something with? So, you may have your calculus sitting in there, it might be getting pretty rusty. That's okay, but I want to see that you can take that calculus wrench and use it over here some way, and that you've done something with that. That to me shows that you've learned something and you've applied it, because we're very much an applied astrophysics. Astronomy is very applied astrophysics, so we need that connection. And it could be, we've had students who've built their own chainmail, that we consider that kind of grit. They have hobbies that are interesting, somehow showed us that they've built something, whether it be a computer code or whether it be something else. We look at all that together. All of that is interesting to us.
Do you think there's any room for independent work? Like, let's say the people who didn't make it.
That's a good question. Independent work is kind of hard in modern science. People might say, we have this all the time. Students come to us, I get this great plan for black holes and gravity. And that's kind of been done for the last 25 years. You didn't look at the literature. The literature, what's been published in peer-reviewed papers is huge. And students usually haven't researched that enough. And so it's hard without the experience of a researcher like myself or someone who's been in the field for a long time to know to sort of guide that. So independent research by themselves is really difficult. A student can come to me and say, I'm interested in this. I'm like, oh, that's interesting to me too. Let's work together and try to understand the problems. And that takes a little longer, but that's a better process than I'm going to solve gravity today. That's not likely to work out. And we get a lot of students. I get a lot of emails from students or someone who wants to prove to me X, Y, or Z, and I can publish this result. I can help them publish it. And usually it's not useful information. It's silly.
But you do have to be optimistic in the sense with the aliens, because in one of these emails, one of them will be like the next Einstein or Ramanujan from India.
Yeah, possibly.
How would you
discriminate?
How do you make sure that you don't miss those people?
That's a good question. So it's a matter of time, for much time I have around, right, to look at these. The emails are usually clear. They're from people who have not thought very deeply about the subject. I do look at them casually, and I get things from people who flat Earth believers or this hollow Earth, things like that, and I get these sort of things. And you can tell very quickly if they are serious or not. It doesn't take much, and I've never seen a serious one in my time. I get a lot of them, and now sometimes they get mailed to the entire department, and those are very unlikely to be looked at seriously because they're just emailing everybody. It's obviously not been well thought out. Because if you're doing some topic, you want to send it to people who are the researchers in the field, right? So I say we do look at them casually, but most of those researchers are going to go through different channels. The people who you're talking about have, maybe not Ramanujan particularly, but Einstein for sure went through regular channels.
Right.
Yeah, and even the mathematical prodigy went through the right channels too in some ways, and he went through the process and had some examples to show of proper designed mathematical results in a way that was more closely related to publishable results, I think, than others. Today, it's a different world, right? Because we live in a world where anyone can access these papers easily on the web, and people can access the data easily. Like for astronomy, in the US, we have something called an open skies policy, which means anyone in the world can use our telescopes. If you propose for it, anyone. If you propose for it, you can use our $1.4 billion telescope if you want. You just have to apply through it the normal channels, and we even do blind evaluations now. So if you want to submit a proposal to observe this galaxy you think is weird, you can do so. And we don't even know who you are. We won't know that you have no experience in it. We don't know. And you could be from a different country. We don't know. And so we give a certain percentage of all of our time to anyone who wants to apply. And so we are very, and that, one reason for that is gender equality. In the past, people were looking at names and they saw, women were getting less proposals accepted than men, or people, international students were getting less proposals accepted. And so we got rid of it completely. So now you cannot say who you are in the proposal. We're very careful about that. We think that gives more opportunity for people who are maybe not in the field. But again, independent research is very rare because it's not something you can just jump into. You've got to build up that knowledge of what's in the field already, especially in astronomy.
And I don't know, but because of the blind acceptance, like, has those things changed?
How it changed in terms of independent research, or with women?
Yeah,
for example?
women
Yes,
and
definitely.
international people.
Yeah, it's increased. Yeah, so we're now seeing a much higher percentage of women getting proposals accepted. It's not just the established old faculty who are getting these now. It's more everyone. We're seeing a much higher increase in diversity in our proposal acceptances. Yeah, and that's good for us. That's great, right? We want that. We want the science. We want the astronomy to be the main point here. We don't care who's doing the science. The best science should be getting done, and I think that's becoming more and more true. It wasn't always true. Astronomy, I think, more than some other fields, have worked really hard to open ourselves to more diversity, more inclusion, and to make ourselves better. I think so. And it's not perfect. It's not. We need more representation in the faculty. We need more representation in research. But it's improving, and I'm optimistic.
What gets you excited about the future?
New telescopes. New telescopes kind of get me excited. They're doing such cool things. JWST, as much as it costs, how much of a pain it was to get launched, is just making some gorgeous images. We detected some new stuff. We got involved in a few projects, and we're detecting these gorgeous new outflows, and new things are just popping up all the time, and that's just so cool.
Do you need to put in a proposal to get JWST time?
Yes, same as before. It's double blind, so you don't know who's submitting the proposal, and people have to read the proposals, and it's effectively, it's very hard to get. I think right now it's a 1 to 5, so about for every 5 proposals, 1 might get accepted, or maybe worse than that. It might be like 1 to 8, I guess, something like that. It's very competitive, and you're competing against people in the world, right? Everyone in the world is applying for JWST time, not just people in the U.S. So we're all applying for this limited amount of time, and so it's only the best proposals we're getting in.
What's the time wait between the moment you put in the proposal versus when you
get the data?
Yeah,
it's about a year.
A year? Sometimes,
yeah. Depends on when it could be quicker than that. It could be a few months, depending upon if you're lucky. But it's scheduling-wise, it typically, on average, I would say about a year, since until the data comes out. Yeah. Wow. Takes a while. But modern astronomy have professionals who look at the data and help you fix the data. There's always going to be artifacts and problems in the data, and it's much better now at pipelining and getting real usable results out very quick. So I think we're getting quicker, even though that time's taking maybe longer. It's being faster to get science out. And it used to be proposals every twice a year or 3 times a year, but that's very expensive in terms of the infrastructure to support that. Right. So one of the reasons we've moved to once a year is because of funding. And so it's just become that, now there's a 1 year, can be a 1 year plus time to the actual get the data. It's, I think, still being better off system. It can be problematic for graduate students, though.
Yeah, because 1 year is just...
Yeah. But usually we have data. So usually when you get working with a faculty member, he or she has data laying around, and so you just start with that data that you haven't published yet and try to get papers out while you're working on, because you got to get to speed on the science, right?
Right.
You have to know what's important in the field and work your way up. So it ends up working out okay.
If you had to, suppose you could touch, smell, and hear astronomy, whatever that means.
Yeah.
how would our understanding change?
Right now we're limited by resolution, right? How big we can resolve these things and see them. So we're always struggling. Everything we're doing is always struggling, whether because we're doing something new that this telescope can only do, but now we're struggling to get down that last little bit, to get the last resolution, the last little sensitivity. We're trying to now resolve these gaps. We're looking for disks around planets now. These things are the edge of our ability to do. And so that's what's kind of the exciting aspect, is that as you push farther, we're getting closer, we're touching these things, and at least metaphorically touching, smelling what the atmosphere, what does an ISM smell like? What are the molecules that make up gas in the galaxy? We found some crazy things in the last few decades, right? We found there's alcohol in space, there's water in space, there's poisons in space, there's urea in space. All those interesting molecules, what would that smell like? It would smell horrible, I'm sure, but it'd be so cool to smell, right? Understanding what molecules are in this, and now planets are forming in that mess. So how does the chemistry of life depend upon the chemistry that's in space? Because forming, for example, the fundamentals of biochemistry is called reducing atmosphere, for example. How we form the conditions for life is very similar to the conditions in interstellar space. And so it's possible that a lot of that initial chemistry that we think of as fundamental for biology might have began in space and transferred down to planets. And so touching, smelling, all that would be so cool to understand exactly what we're dealing with and recognizing the molecules. We're doing it from afar. We are doing it. It's a difficult time. We're always scratching at the edge of technology.
So astronomy, in many ways, is looking up. Do we have an effort to look down and have like telescopes to?
We have lots of telescopes looking down, but they're all run by the U.S. military and others. Spy satellites look down.
And hold on to that, because I don't know what you mean by that, but I mean like looking down as in, going to like the microscope, like
that would not be astronomy. You'd probably be in geology or oceanography.
It would be like you like looking down, like let's say like here, and then like going.
Yeah. I mean,
we have such thing.
I mean, we do have something like that. For example, astronomy has that for Mars. For example, we get pretty high resolution imaging of Mars from satellites. But looking down, astronomers aren't doing that. That's going to be mostly atmospheric scientists, for example, or oceanology. I mean, we do not have a very good map of the ocean floors, for example. Still, we don't have good understanding of the interaction of weather, and so there's lots of places here. Remote sensing, which is what you're basically talking about. You're talking about sensing things from far away, is being done in numerous other fields besides astronomy, and we use very similar techniques and processes. So there's an analogy there, but astronomers don't do it. But spy satellites are basically, there's a Hubble Space Telescope that's looking down right now, I'm sure. Something that's equivalent to Hubble Space Telescope looking down on Earth, and it probably uses very similar technology to what we use. It probably uses mostly optical, but it might use infrared too to look for certain things. I don't know what they're doing, not involved, but they are using exactly the same tools as astronomers use. It's different technologies. And so in astronomy, for example, we have different technologies too. We have optical telescopes that work in the optical visible range. We have far infrared telescope, which work in the far infrared optical. We now have gravitational waves that are being detected that operate different. We have astroparticle detectors, so like you can detect neutrinos, for example. We have now more techniques to study things that are far away than ever before, and some of them are light, but some of them are not now. Like I said, gravitational waves are a completely new type of science, and so all of this is different that astronomers now have access to they never had access to in the past. So that's all changing and kind of interesting, and that same technologies, again, are being applied to different studies on Earth. Yeah, but they have, of course, different needs, different issues, and so forth.
What advice do you have for someone who's smart, motivated about how they can go and live a life that they're full of meaning and
enjoy? Well, I think you have to find what you're really interested in. And that's hard today because there's so many subfields. It's not just, it might not be astronomy particularly, it might be this part of astronomy that really excites you. And I think that's the hardest part today, is finding out what really excites you and gets you interested, and then build those tools. Building the tools is a critical component in today's society. If you don't know how to use Python, or you don't know how to use these packages and use them, it's not that you took a class. I don't care if you took a class. I care that you can use these tools to solve problems. I need problem solvers that can demonstrate quickly that they can use this to solve this. That to me is developing those tools, seeing what you're interested in, getting out, trying different things, doing programs, that may be related but not exactly. You can sometimes find gems that you never knew existed, and you can find really great programs and great faculty and researchers that you never thought even existed before. And that can be hard. And it's going out, taking classes, taking gen eds, being interested in the world, not worrying about your grades being perfect. Exploring. If you have a 4.0 average, you're kind of wasting your time. You're not getting out and doing things that are interesting, that you could be understanding more about yourself and the world. That's my feeling.
I like it.
And then at the end of our show, we have a section called overrated or underrated. So we give you a topic or a statement, and you tell us whether you think it's overrated or underrated.
Okay.
So the first one is the naming of the planets, like overrated or underrated?
Underrated. I don't care about the planets' names. I don't care if it's called a planet. I don't care that Pluto's no longer called a planet. Call it what you want. I don't care. It's a body that got formed. That's all I care about. I don't care about if it's called a planet or a dwarf planet. To me, is not super relevant. Names are names, and people get caught up on names so much, but I don't think it's that. That's not part of the science. The science doesn't care what you call it, right?
That's true. Like what I think is, like, let's say an alien civilization is looking down on us, right? Our planet. They probably have their own names for.
They have their own names, yeah.
Earth, Sun, Mars, Jupiter, everything, right?
Yeah, every civilization on Earth even has its own names.
Exactly.
Why we've chose this one group, and it's a bit of exclusive, right? We've chosen what we think is more of the Greek names for constellations, for example. But there were lots of other civilizations that had other names that were just as good. But we seem to have chose that one because of what civilization became the most dominant. But we shouldn't be teaching that. I don't teach constellations very much in class because they're just stars with names built on. I kind of care about them now because I need to know where they're at in the sky, so I know where Orion is this area. But the constellation name is not really relevant. So I have a bit of a pet peeve about this anyway. What happened to all the good indigenous names of constellations? We've lost all those. So anyway.
Is there do you have a favorite constellation? Because for me,
Orion always.
Yeah,
It's got to be Orion. Orion's gorgeous. I was just recently on a beach somewhere with a very dark sky, and you could see the nebula, Orion Nebula, so nicely. And here you can barely see Orion at all. So it was great to see that. I love Orion. It's fun. But I love seeing Orion from the southern hemisphere. You should try that. Because it's upside down. It freaks you out. It freaks you out.
Upside down.
Everything is weird. Everything is weird from the southern hemisphere. So I've been to. I remember observing once from Australia, and it was so cool.
That's a good point.
Yeah, and then seeing the LMC, Large Magellanic Cloud, and Small Magellanic Cloud, which are nearby galaxies of ours. And the night sky, they're so cool in the southern hemisphere. Southern hemisphere is really cool. Most astronomy is done in the southern hemisphere now, because of our big observatories are mostly in Chile. Yeah, so the big telescopes are mostly being done from the southern skies, and we have the telescope in Antarctica, the South Pole Telescope, for example. So a lot of things are being done from the southern hemisphere nowadays. And ALMA, which is where I observe, is from Chile. So there's lots of great science being done from the southern hemisphere now.
Is there any benefit for doing it from the southern hemisphere?
No, it's just location. We want to be high on a mountain with low water column.
Okay.
And so Chile happens to be a great site for that. Hawaii is great too, but Hawaii is limited by how many telescopes you can have on the mountain. And there's also a good place in the Canary Islands. But there's not a lot of great places for telescopes. I mean, except for space, and space is much more expensive.
We'll make one on the moon.
Yeah, I'll make one on the moon. That's what I'm saying. Gotta go to the moon, yeah. I want to visit the telescope on the moon.
Who wouldn't?
That'd be super cool.
Yeah.
Yeah.
The thing is, you wouldn't be able to see it from here because if
it's on the far side now. You can't see it. Not the dark side.
The
far side, yes. Okay, keep that in mind.
Yes.
There is no dark side.
There is no dark side. Pink Floyd.
Pink Floyd is wrong, yeah.
The next one, Project Hail Mary.
Overrated.
Really?
I think so. I think there's different different techniques and processes that we can do. Unless I misunderstand what that means.
What are you thinking of?
I'm thinking it's a project to save humanity, basically. Am I wrong?
There's a book called Project Hail Mary.
Yeah, which is the
right
way to save.
Like this is a fictional book.
Yeah.
Right.
I understand. Just like the three-body problem, which is technically a fictional book too, but has some interesting things for aliens too as well. Yeah. So maybe I don't know the topic that well. So explain it to me a little bit.
So I was referring to there was a
Which-
book that came out, I think, 2 or 3 years ago,
Right.
called Project Hail
Right.
Mary.
Right.
Amazing book. It was about how the sun was dying.
Right.
There was some
Yep,
leech
Yep.
on the sun, and
Yep.
they had to find
Yep.
a cure.
Yeah, that's what I thought. Okay.
Right.
Yeah. Overrated because it's mostly junk science, first of all. Overrated mostly because there are real problems, real astronomy issues we're going to have. That one, an asteroid coming in could hurt us really badly at any point. A small asteroid could take out Chicago, and we wouldn't even know about it much. That's changing now. We had DART recently, which so we have that issue. We have the sun evolution happening. That's going to be a problem in a billion years. Those, to me, are fundamental. We need to think about ourselves and what we're going to do problem. That problem, I understand the Hail Mary concept here, again, saving humanity from this disaster, is fun to think about. It's the same kind of problem. But there are fundamental issues we have to do. And so overrated because we need to think about humanity needs to get off the Earth. We have all of our proverbial eggs in one proverbial basket, and one asteroid takes us out. In less than a billion years, the sun's going to be too bright for us. We have to get off this planet if we want to be a true advanced civilization and last a long time, more than 100,000 years or whatever. So to me, that's the fundamental aspect. Really, we have to get off the planet. So having our eggs in one basket, which is that case again, is the problem. We need to get our eggs out of this basket in as much space as possible. So Mars. A future, and again, this all comes down to money. It comes down to initiative and need and priorities of a civilization. But at some point, we have to get off the planet. We have to have colonies on other planets if we want to survive. And then eventually other star systems. Again, I'm not sure it's even possible, but that's something we have to think about and try.
Science commentators such as Neil deGrasse Tyson or Carl Sagan, overrated or underrated?
Underrated. They get the info out. They inspire a lot of scientists too, right? They inspire the next generation of scientists. We're the first generation, maybe the second generation, who've been inspired by Star Trek, by Star Wars, and that plays a larger role. That kind of input into the scientific community, whether it be nonfiction or fiction, is critical to keeping the community enriched and prosperous in many ways. That drive that they exhibit, I mean, they're great talkers. Both of them are able to have emotion, and they are able to talk about these great ideas. And that inspires others. And Neil deGrasse Tyson, being underrepresented, he represents a larger group. He able to inspire people. I can do that too. That we need to be a really vibrant community. And so, underrated.
Stephen Wolfram's A New Kind of Science.
I don't know much about that topic. Remind me what his argument. I know you had a large discussion.
So the cellular automata
Yeah.
was like the main idea behind the book, which is that the universe, it was all born out of a very simple thing at the beginning. Like, even though universe is
Yes.
complex today, but it had very
It was simple in the past, yes.
and it just like mutated
Yes.
evolution, and it just like it
Yeah, I think that's overrated. I would think any cosmologist would disagree with that, but I don't know I'm not a cosmologist.
right.
My first thought is that's overrated.
What do you think is the more probable explanation?
I think the more simple explanation is physics. That physics happens, and physics drives it. And maybe we don't understand the physics, or we don't understand the conditions, but physics drives everything. Maybe he's saying that. I don't know what his. I mean, I've heard this before. I've not looked into it much. It's not been well peer reviewed, to my knowledge, which is always the gold standard for us for science, right?
Then the last one.
Good.
Oktoberfest. Overrated or
Oktoberfest.
underrated?
Underrated. I love Oktoberfest. I love it.
Do you have any favorite memories?
Yes. Mostly getting on tables and singing. I think 3 times we were there the first day with friends who were really good, and they went and reserved a table, sat at tables for us. And so we got there the first day. At the very time we were there for a couple hours, and then they do the traditional tapping of the beer keg. Boof, douche, douche. And then the barkeep people run out with all these beers, and they were, I don't know, she's carrying like, I don't know, 15 of these 1 liter Moss beers, and it was just so cool to watch. They go, douche, douche, and then they run out with all these beers and drop them on the table, and they just keep going on and on. It was so fun to watch. And I really like German beer a lot. So it was with good friends. And then the music, there's lots of good music, and you're getting up on tables and singing songs and dancing. It's a lot of fun. Some people hate it. It can be very crowded and annoying, but I have very fond memories of Oktoberfest, and I try to go back when I can.
Oh, nice.
Yeah, I've gone to maybe 6 of them.
Wow.
Yeah.
Well, thank you so much for coming and talking to us and teaching us everything you know.
I unfortunately am not the interesting person that you need, but interesting person you had anyway. So you're welcome.
No, it was truly our pleasure to host you and just to ask these questions, because you don't really, like, we think about these questions, but we don't really think that hard about it, right? Until you ask someone like you who might have also thought about it and has something valuable that they can share with us.
Oh.
And as you mentioned, it's a beautiful universe that we live in, and we should be grateful of everything that we've been given, and just the factor of life is just so exciting in itself. And
Yes.
aliens may exist, may not exist, but just this gift that we've been given to think about these questions, ponder, explore,
Exactly.
and just try to get at the root of all these things that have gotten us where we are today. I think that's just a beautiful thing. And
Agreed. Yeah.
I cannot thank you enough for all the research and all the work that you're putting into getting us closer to the answer, and just inspiring the next generation, which is us, by maybe teaching a course on extraterrestrials or anything exciting, anything that's gonna change the future, that's gonna define the future. So thank you so much.
Oh, you're welcome. It's fun. I enjoy it. Great.
Awesome.
Yes, I've transported myself to a different galaxy now, and I'll let you enjoy. I hope you enjoyed this conversation. If you did not, I hope you enjoyed this conversation. I want to tell you about a few things that I thought that I would like you to maybe also consider. Is that I know you may be busy with school, your job, with whatever it is going on with your life. I think it's really easy to get busy with things, and we don't ask ourselves these questions about what is the universe, what is beyond this earth, what is the earth, and all these questions that are very simple that we often asked ourselves when we were young. And what happens is that we somehow forget to ask those questions. We get busy. And I think fundamentally we know that there's something out there, and we know there's more to our reality in a sense. And I hope that you spend some time. You basically just spend some time thinking about these questions and don't just get carried away by life, and be curious in whatever way you can find. Lastly, I'll tell you a story to end this. Is the other day I was thinking, okay, if I were to ask different people, depending on who they are, where the universe came from, someone might say, okay, it came from the Big Bang. If I were to ask someone else, they might say, oh, it came from God, or came from some sort of thing. What it made me realize is that both of the answers are sort of the same, in the sense of they tell you an answer and you cannot ask anything beyond that. Where does the universe come from? The Big Bang. But why the Big Bang? That's it. Where does the universe come from? God. Why? God. And that's weird. It's just sort of like an answer that you cannot question, and you're supposed to somehow accept. And maybe something there. Maybe we're asking the wrong questions, but I'll leave you with that. Think about where the universe comes from, where it might be coming from, where it might not be coming from. And it's really about the questions. So what questions are we not asking? what are the wrong questions we're asking today, and not just about the universe, but even about your own life. Yeah. All right. Thank you. And I'll see you next time with the next episode and the next and the next and the next. All right. Thanks.